Morning. So we are in a new topic today called root locus. And the root term is expression we already know, right? Root is the square root. Locus is, I don't know if that's a Latin-based term or a math-based term, but essentially it's a plot of all the roots for a potential characteristic equation. So in the title, it's actually telling you what we're trying to do. So one of the elements of design is we're trying to get the characteristics of a system that we want. And part of it is we have a variable gain parameter, like in the case of a proportional controller. And by varying that value of K, oh, excuse me, I hadn't coughed all morning and now I start coughing. By varying that value of K, we hopefully will be able to move the roots of our system to the location to get our desired operating characteristic. Now, when we do a root locus plot, we're actually going to be able to get all the roots of our system, but we actually are going to limit our value of K so that K is going to be greater than 0 and not less than 0. All right. And there's a whole bunch of reasoning behind it, but the ultimate reasoning is if you have a proportional controller, it's unlikely that you're going to have a system that has a negative gain coefficient with it. It's almost always going to be a positive number. So we'll keep their values of K to be a positive number. So it's only for one parameter controller design. Again, that value of K, which is a real number, okay? That's the most important part. So this value of K, let me move this up over here. There we go. This value of K is variable or adjustable. It is a variable that you can specify whatever value you want. And we're going to go ahead and move it around to get the operating characteristics that we desire. All right, so let's do brute force, right? We can always do brute force, and we have computers that allow us to do, brute force really efficiently. So here is the transfer function of any closed loop system that we have. And remember, the characteristic equation is the denominator of our closed loop transfer function. So we want to solve for the roots of our characteristic equation, and we're going to allow K to vary. So let's start. Let's start with K equals 0. We have S cubed plus 4S squared plus 0S plus 1, right? We just substituted K equal to 0. We run that into MATLAB, and then we have our three poles for this closed loop system, -4 and plus or minus 0.03 plus or minus J 0.05. Go to 1. Now K equals 1. We have S cubed plus 4S squared plus S plus 1. Run it over to your calculator or MATLAB, and then here are the roots that we have. And you can see that the roots have changed, right? They were -4 and then +3 plus or minus J 0.5. Now they're -3.81 and then -1 plus or minus J 0.5. So they are changing as we vary K. Let's try 2. S squared plus 4S squared plus 2S plus 1 gives me roots of here. So not only is this root here, I guess it doesn't want to wake up. We should change the battery, but this is a new battery. I don't understand why. It's almost like you have to reactivate it. So that number, the real part of, or the real root that we have, we can see it's decreasing, right? Or increasing, depending on your perspective. It's getting less negative. And up until we got to 2, we noticed that this term was staying the same. The complex term was staying the same. Now we're starting to see that our complex number is decreasing, right? Or again, increasing because it's getting less negative. The one thing that's important to note when you're looking at these things is you always, always, always have complex conjugate pairs, all right? That is a requirement when you do S-plane plots. You can't have a plus J term without the minus J term. So even if I didn't put this number here, if I left it out, you know it has to exist because you have to have a complex conjugate. let's do 3. So again, now k equals 3. So we have s squared plus 4s cubed plus 4s squared plus 3s plus 1. Check my roots. And let me move this line out of the way so we can make out what's going on here. And again, we're getting some changes. Do 4. This is our last one. Now we have 3 real roots, right? We no longer have complex numbers, so we no longer have a second order system. We have 3 first order systems. And all these poles are negative. And what do we say about left-hand half plane, right-hand half plane? If we want a bibostable system, all of the poles have to be in the left-hand half plane. When the case was k equals 0, I had 2 positive numbers there. So this was an unstable system. When I went to k equal 1, then I had only negative numbers for my real part, right? So that dictates on my pole 0 map that would be a stable system. However, maybe I had too much overshoot, right? If I have a second order system, it's possible that I can have too much overshoot, or my settling time is too long. We don't necessarily know. And then I kept trying different numbers until I got perfectly real roots, which means I have no overshoot. And because all those numbers are negative, then I'm good to go, right? Maybe I met a certain design criteria that I can't have any overshoot in my system. The problem with the system, though, or this approach is I had to plug in 5 numbers. It's a lot of work, right? What if I had to plug in 400? Would I just keep going? 5, 6, 7, 8, 9, 10. It gets tedious after a while, doesn't it? And with computers, you could certainly do a while loop while something is happening, keep incrementing the number until we get to a value. But again, that requires a lot of work and a lot of coding to go ahead and set up. So let's do, oops, I added the 5 in here. And here's the other thing too, right? So we see when we go from 5, we went from a stable system, all negative numbers. There's a typo here. That should be a negative number here, right? Because you can't have a negative. Well, let's check. Let's run a MATLAB. You all remember how to do roots in MATLAB? So we just type roots of, and then we put in brackets the number. So we have s squared plus 4, s cubed plus 4s squared plus 5s plus 1. So we just put the coefficients 1, comma, 4, 5, and 1, close the bracket. And that should be a negative number. So let me go back in here and fix this. Oh, I gotta get rid of that. Why aren't you allowing me to change? Looks a little weird, the format. I'm not sure why it's not formatting it correctly, but that's okay. We get the negative number in there. That's what matters. So let's go back over here. Okay, and then duplicate this. Okay, so still a stable system, but now we have some overshoot. So maybe we don't want to increase it past 4. Maybe we want to stop at 5. So again, just kind of a tedious work. Here is what happens to our system. Here are all the poles for all these different values of K. This image here will actually show you, watch what happens to K. Look at K as it's increasing. You can see the X values are moving along. Until they get to the real axis, then they start going in opposite directions. Continue to increase, and then they become complex again, and you can see they go away. So let's see that again. Watch as K increases. And again, this is just trial and error. This is brute force, right? Just plug in K, equal those values, and then just keep plotting until you get to a value. So this is just done with a while loop, right? And you let K increase by 0.1 each time, and then you solve for the roots, and then you just do the plot. So hard to see, but this is the value, that was the value of K equal 50. So again, let's do a little more systematic or structured approach to actually finding those values or drawing them with some accuracy. First thing we need to do, why do we need to do this again? Remember our whole zero maps for second order systems? We went and we showed you how we have plus or minus j omega d. What does omega d stand for? What is the expression omega d? We just had to solve for this on a test, right? You didn't get it right? So can I take 5 points off on the test because we don't remember what omega d is from just 5 short days ago? I guess that's
Is
a
it
yes,
the damping
right?
frequency?
What's that?
The damping frequency?
Yes, the damped frequency of the system. So when you have a second order system that has a zeta greater than 0, but less than 1, that has damping associated with it. And so its natural frequency is different than its damped frequency. So omega sub d, it actually shows you right on the image, right? Or on the presentation. It shows you what omega sub d is. It's omega sub n times 1 minus zeta squared. This value right here is always the real part, right? And what was this value again right here? You all remember what that is? You know? Not E of S, no. We can do the hypotenuse, right? So we can have the real part squared, zeta omega sub n negative squared, plus omega sub d squared, and we can square root that, right? But we know omega sub d is equal to this. So that's equal to the square root of zeta squared omega sub n squared plus omega sub n times 1 minus zeta squared. That whole term is squared, correct? When I substitute in, this is equal to the square root of zeta. Oops, I forgot the squared term squared. Omega sub n squared. Plus omega sub n squared. What happens when you square the square root of something? Goes away, yeah. So you just have 1 minus zeta squared, right? And hopefully what you see is all I'm left with is a square root of omega sub n squared, which is omega sub n. So this here is omega sub n. What is this angle equal to? What's theta equal to? Come on, Oscar. Maybe I have to take 10 points off the test. Can't do what a right triangle is. You can't calculate theta. Oscar had a heap be adjacent over the hypotenuse. So the cosine of theta is equal to the adjacent over the hypotenuse. It's just zeta, isn't it? And I don't have to worry about the negative sign, right? Because all I'm looking for is an angle. So it doesn't matter that it goes in this direction or the other direction. I'm still looking for the angle between the two. So the cosine of theta is equal to zeta, right? And that was important for us when we looked at second order systems to be able to start to pick out some characteristics that we were looking for. So always complex conjugate pairs. What is the line of constant T sub S? We went through this already, a settling time. Constant T sub S means it settles out or reaches 5 time constant at a fixed value. This here is e to the minus, or I should say minus t, right? So the only thing that's going to affect its settling time is the zeta and the omega sub n term. What about the line of constant zeta? We already know that, right? This line here has to be constant because if zeta doesn't change, the inverse cosine of zeta is always going to be a constant angle. So those are constant angles. What about constant omega sub d? Meaning this way, back and forth, is constant. Then your imaginary term is constant, but that only means what the oscillatory frequency is going to be. So if you have a constant omega sub d, it's only going to oscillate at that specific frequency. What about omega sub n? That means that we have a constant radius there, but that's not all that particularly useful for us. We usually don't worry too much about that. What about a constant tau? Again, that's the same thing as the time constant. What about percent overshoot? See if I can move that off to the side. Percent overshoot is exclusively based on zeta. So that means we have a constant zeta. And that's how we do that. All right. Complex number math pros. I want you to take this number here and solve. I would like you to tell me the magnitude of angle and solve for that. How would you do that? Well, the first thing I would do is I would plug in -3 plus J4. So -3 plus J4 plus 1. So plug in -3 plus J4 for S, right? All over -3 plus J4 multiply by -3 plus J4 plus 2, correct? If I want to solve for the magnitude and the angle of my transfer function at any particular point, I just plug it in. And this becomes -2 plus J4 all over -3 plus J4 times -1 plus J4, right? Now, you can stick this in your calculator, right? And you can go ahead and solve for the magnitude and the angle. But what do we know about complex math? We know if we have coordinates in rectangular coordinates, we can just do regular math, right? We can add, subtract, multiply, and divide. We already added and subtracted here, right? We already added real and imaginary parts. Now, we can multiply these two, right? So we can FOIL those two and come up with a number. The problem with that is that's not necessarily an easy FOIL, is it? And the reason why it's not easy FOIL is when I do the last, J4 times J4 is J squared 16, which is actually equal to -16, right? You have to make a substitution. What's a better way to multiply and divide complex numbers? You used to have to do this back in the old days with your calculators. You couldn't do it so easily. How do you multiply or divide complex numbers? Let's write it generically. I have a magnitude and an angle, and I want to multiply that by that magnitude and angle. How do you multiply complex numbers? Yes, sir. They are in polar, right? The M1 and theta 1 and M2 and theta 2 are already in polar. We're not talking about this part right here. I just want to go ahead and I want you to tell me how to multiply those two complex numbers together.
Don't you multiply the M values and then you end up dividing or subtracting or adding the angles?
Close. multiply the two magnitudes, and then you add the angles. Do you not remember this from even John, right? I think in John, when he does 312, he does a lot of this, doesn't he? So this should not be new, right? Haven't done it in a while. How about dividing complex numbers? Rita, you can't, because you've been so helpful. Rita gets the star for the day because she's the only one answering questions. Everybody else gets negative stars. What?
So
How
I
do you
keep my test
divide by?
points.
Brandon,
Put n over 2 and then you subtract the two thetas.
M over 2,
M1 over M.
and then what?
Take your theta 1 minus theta 2.
Yeah. You subtract the angles. Okay. So doing this, you know, it might be a lot of work to get complex numbers, but generally speaking, it's much, much easier to divide or multiply complex numbers using magnitudes and angles. Okay. So going back to our presentation, I'm going to go ahead and do these individually. So S plus 1, which is the 0 associated with my transfer function. When I plug in -3 plus J4 into S plus 1, I'm going to go ahead and get -2 plus J4, right? Now, let's enter that into MATLAB. So I have, let's call it, we'll call it 0.1 or 0.1 equals -2 plus J4. Okay. Now I want to double check if I get magnitudes and angles. So the display for Z1 is going to be equal to the absolute value of Z1 and the angle of Z1 times 180 over pi. Plus I didn't put the divide by. Or multiply by. So I got 4.47 at an angle of 116.7. Let's check that over here. I got square root of 20 at an angle of, we'll call it 117. Let's check and see square root of 20. 4.4721, right? So that is equal to that angle. Okay, that's the magnitude and angle for the 0 at that value. Now, I'm going to do this one. So this is just an S value. And then when I plug that in, I end up with 5 at an angle of J127. I do the same thing for S plus 2, this one down here. And I end up with square root of 17 e to the J104. So when all is said and done, what I'm going to do is my transfer function evaluated at S equals -3 plus J4 is going to be equal to square root of 20 at an angle of 117 divided by 5 at an angle of 127 times square root of 17 at an angle of 104. And if I do my complex math, I end up with square root of 20 over 5 times the square root of 17 at an angle of 117 minus 127 minus 104, right? So if I divide by multiple numbers, I just keep subtracting. Okay. That should equal 0.22 at an angle of minus J114. Let's check that. Let's go back to MATLAB. And I'm going to enter in S equals -3 plus 4i, right? That's my S value. Now, my G of S, so I'm gonna just call it of S, because you can't actually put parentheses, MATLAB will burp at you, is gonna be equal to, I have S plus 1 divided by S times S plus 2. Now, I gotta make sure I have parentheses. And I get, if I entered it in correctly, I get minus 0.0894 minus J 19.19761. Let me make sure I've got that. I think I'm good. Now, let's just check to see if that's correct. And I'm just going to put just display G. That is going to be equal to the absolute value of G of S and the angle of G of S times 180 over pi. Oh, I forgot to put close brackets. And I get 2.16 at an angle of minus 114, which is exactly what I get here. Let's take a look. Because I don't actually show the math. Let's take a look and see what the square root of 20 divided by 5 and 17 is. So square root of 20 divided by 5 times the square root of 17. .2169, right? Now let's take a look at the angles. So I have 117 minus 127 minus 104. 117 minus 127 minus 104, correct? I think I got it right. Minus 114. What do you know? I get exactly that same answer, whether I do it all at once or when I do complex math. So what this tells me is this approach for solving for the values is actually going to be correct. It's going to give me a correct value. So I'm feeling pretty good. And it shows now, so what I can do is I can actually show the individual angles. So I'm going to pick this root right here, right? This is -1. So this angle over here is 117 degrees. And this magnitude is the square root of 20. That's the magnitude and the angle that I need to go to get from -1, the 0 of the transfer function, all the way to -3 plus J4. I can certainly do it this way, right? I can do the hypotenuse, the square root, magnitude of the -2 plus J4. That's just by doing it the brute force way. I don't necessarily need to do that. Now I'm going to go ahead, let me erase this. And I'm going to go ahead and get the magnitude and angle from -3 plus J4 to that very first pole that I have. The magnitude is the square root of 25. Or 5, right? Square root of 25 is 5. And that angle is going to be a positive 127 degrees. It might not be obvious, but if I go back over here, you can see that that angle is 117. That's slightly less of an angle than this one here. Okay? And so you can calculate, would you calculate that angle by hand? Any ideas? What's the easy way to calculate the angle? Anybody want to guess? You trig gods, you. Can I calculate theta? I know that and I know that, right? And I also know that. If I take the inverse tangent of the opposite over the adjacent, remember Oscar, right? The opposite is 4, the adjacent is 3. What's the angle that I get? 4 divided by 3, and then I got to multiply that by 180 over pi. What do you think that's going to be equal to? It better be equal to 127, right? Or is it? Let's see. Nope, it's not 127. It's 53. So is that a mistake? No, it's not a mistake because it's 53 from here. The angle that I'm rotating it is always the 0 angle, right? The 0 degree one, which is perfectly right. So this angle right here is 180 minus 53 or 127. Okay. So you can also do this like this brute force approach. And then lastly, is this one over here. I encourage you to practice this on your own to see if you can come up with the magnitude and that angle. We didn't actually show you how to do the angle on this one, but we showed you on the second. So again, you can do it individually. And then the sum of those is going to be, whoops, the actual magnitude and the angle for G of S at that value. All right. So it's a point entering that specific point. Here's how you want to do what's called an inline function in MATLAB. You can actually do inline functions. So I'm going to define my first point, S1. And then this inline function here means I can actually just say G is going to be equal to this value. And then it's an inline function because of the ampersand sign. And what happens is you pass it the value S or a value of S. And then you plug it into this equation over here. And you can see once I call G, MATLAB understands it as a function call, and then it just passes whatever value is your variable you have. So if you run this through in MATLAB, you would go ahead and get it, but it would just be a little bit fancier. Well, let's see, can I copy this from here? I think I gotta copy it here. And let's copy it over. Paste it into MATLAB. Let's do a new script. Right, and there's an error here. Oop. Giving me an error. What's the problem? Ordered vector. Do I need a semicolon though? Only if I don't want it to display. There. It automatically copied in the weird one, I think. Although it's still giving me errors. Well, let's just do this. And then let's see if we can run it. Let's move it to this class. Let's bring up MATLAB. So that just prints it nicely, right? So the value G at S equals -3 plus J4 is equal to 0.217 e to the minus J 114.3 degrees. Okay. So if you want to do with inline functions, that works really well also. All right, let's get this back going here. Oops, I should have brought it to that page. I thought it was automatically there. Guess that's not the case. Make sure that I'm recording. I am recording. Okay. All right, so first root locus rule is actually not even a root locus rule, it's just a pole zero map rule. Your root locus is always going to be symmetric about your real axis, and you have to have that because you have to have complex conjugate pairs. That's the first one. All right, 5 minutes. Get to getting. Go ahead and calculate the open loop transfer function at s equals -2 plus j. I'll give you 5 minutes. I have, well, let me look officially. I think it's 8:36. Yeah, 8:36. I'll give you 5 minutes. I'll actually start a timer. Excuse me. Well, I'll do a stopwatch. I'll just make it easier. Got about half the time left. Got a minute left. 1 minute left. All right, what'd you get? Anybody get the answer? Anybody? Not sure how to do it or just needed more time? All right. So we're doing the open loop transfer function, right? We want to see what that's going to be equal to at that root. So -2 plus j plus 3, that's the first one, times -2 plus j plus 4. Second one, -2 plus j plus 1, -2 plus j plus 2. I'm just plugging in -2 plus j everywhere I see s, right? That's going to be equal to 1 plus j times 2 plus j over -1 plus j times j, right? The -2 and the +2 will cancel each other out. So I want to find the magnitude and the angle of 1 plus j, right? So 1 plus j, what's the magnitude and the angle of that? You can do that in your heads. What is it? Square root of 2, that's the magnitude. What's the angle? If the real part and the imaginary part are the same, 45 degrees, yeah, right? They're both the same, it's 45 degrees. And we already know then, -1 plus j, still going to be the square root of 2, but now the angle is -45 degrees. The only one we don't know is 2 plus j, but that's going to be equal to the square root of 3. And the angle here is the inverse tangent of 1/2, right? What's the inverse tangent of 1/2? Anybody know what that is? I don't. So let's do that up really quickly. So inverse tangent of 1/2 times 180 over pi, 26.6. Whoops. Square root of 3 at an angle of 26.6. Okay. What about j? That's the easiest one. Magnitude and angle. You didn't even have to think about this. Just spit it right out. Magnitude is 0. If it would be 0, then it wouldn't exist, right? How about anybody in TV land?
Square root of -1.
Square root of -1, yeah, but what's the magnitude and the angle? That's the real axis. What axis is this? The j-axis. Isn't it 1 at an angle of 90 degrees? Ring a bell? J is just 1 at it's actually the j-axis, right? So it has to be 1 at an angle of 90 degrees. So now I get square root of 2 at an angle of 45, multiply by square root of 3 at an angle of 26.6, divided by square root of 2 at an angle of -45, and then that multiplies by 90. So what I end up with, square root of 2 times square root of 3 over the square root of 2 times 1, and the angle is 45 plus, because I'm multiplying those together, 26.6 minus, and I'm going to put these all in parentheses, -45 plus 90 degrees. Cancels with those two, right? So 45 plus 45 is 90, minus 90 is 0. So we end up with a square root of 3 at an angle of 26.6 degrees. Are you stupefied or confused? Yes, sir.
So in the previous problem, we had done when you had added or subtracted the angles together.
Right up here, you mean? Or you're talking about those actual numbers here?
We were doing up numbers, it was like, 147, 104.
So we did those in MATLAB.
When there was two values in the denominator together, but you didn't add them together, is that different?
I did add them together. I subtracted them both, didn't I?
Yeah.
I'm subtracting the terms that are in the denominator. So I subtracted the 127 right here. And I subtracted the 104 right there.
Okay. Don't really understand how those wouldn't be added, so they're being multiplied together.
They are being added together. 127 plus 104 negative is the same thing as negative 127, negative 104, isn't it?
Yeah.
Isn't that what I have right here? Negative and negative. It might have just done more subtly.
Yeah, I didn't pick up on that.
That's okay. So yeah, you can always do that with this approach here. Who wants to check my work or check our work? Let's check it. Let's check it in MATLAB. All right. Let's see, I guess, let's see if we can move it over here. So we're going to say S equals -2 plus J1, right? Or I. And then I'm just going to go ahead and just put OL for open loop is going to be equal to, let's see, S plus 3 times S plus 4. And I'm going to divide that by, I'm going to use a bunch of parentheses here, S plus 1 times S plus 2. -2 minus 1. The absolute value of OL is 2.23. That's not what I got. Did I make a mistake here? What's that? You don't think I can subtract the 45? All right, let's do it out in more detail. So square root of 2, square root of 3, over the square root of 2. 45 plus 26.6 plus 45 minus 90 is what I did. Right? When I distribute the negative. And so what I said is these two. Okay. But I get the square root of 3. And did I do that incorrectly? Hold on. Oh. Let's see, S plus 3, S plus 4, S plus 1, S plus 2. So that looks okay. Do I have a math mistake here? I need the what? Oh, yeah. No, you're right. That's not square root of 3. What is the magnitude? It's 2 squared plus 1 squared, which is the square root of 5, not the square root of 3. Thank you. And that means I have to erase this and this and this. And so my final answer is, yeah, you see it's the square root of 5 because these cancel. It's the square root of 5 at an angle of 26.6. So the open loop magnitude is 2.236. What is the square root of 5? Let's get up a little higher. Equal to, what do you know? 2.236. Now let's check the angle of the open loop and then multiply that by 180 over pi. And I get minus 153.43. What angle did I calculate? Positive 26.6, right? I'm not sure why those are, because I know that 153 plus 26 or 153 point whatever. Yes, sir. It's going to reference from 0, yeah. So it would be that way. So I'm getting 26.6. They're getting 180 degrees out of phase from that. So the magnitude works. Let's see what I get over here. Oh, no. Negative 2 plus j is definitely 26.6. This should actually be square root of 5. But it's just off by 180 degrees. I'm not sure why. I get the magnitudes, but the angle is off. Double check this for a second. So I got positive 1 in j, positive 2 in j, negative 1 in j, and those two terms cancel out. Square root of 2 at 45. Square root of 5 at 26.6. Because that's the, yeah, so that's okay. Square root of 2 at an angle of minus 45. I'm not sure why this is 180 degrees out of phase. Go this way. My best guess is that I've got, I am subtracting correctly. I'm not sure. Did I enter it in here correctly? S plus 3 times S plus 4 all over S plus 1 times S plus 2. I'm not sure what the 180 degree is. I'll have to get back to you on that one because it's right there, right? We get the same magnitude, but for some reason we have 180 degree phase shift. But anyway, you get the approach to how to do these, right? Because, and why do we actually want to do it this way? Because we need to figure out when we do our root locus, when we solve for our transfer function, here is our characteristic equation. And what is the rule for having a root that exists on my characteristic equation? What's the rule that we specify? We know that 1 plus k g times h has to equal 0, doesn't it? So for it to be a valid root, this must be true. 1 plus k gh has to be equal to 0. If we plugged in, like in our previous example here, if we plug in a value, we assume k, let's just say k is equal to 1. If we plug in a value and we get not 1, or if we plug in a value and we don't get 1 plus k gh does not equal 0, then we don't have a valid root. So let's go ahead and define that as our term. So 1 plus kgh equals 1. Every valid point has to satisfy that, which means when we solve for kgh has to be equal to -1. What does that tell me? The magnitude of k has to be equal to 1 over gh magnitude, all right, for it to be a valid point. All I'm doing now is I'm converting these into real numbers or complex numbers. So I have magnitude of K is 1 over GH. And my angle has to result in negative 180 degrees, which is also the same thing as plus 180 degrees. And it's also the same thing as 3 times 180 degrees, right? So 540, if I have 540 degrees, that's 360. And another 180 gets me back to that point. So my angle has to be multiples of 180 degrees, right? Those are the criteria for doing a root locus. And it can only be odd multiples, not, why can't it be even multiples of 180 degrees? Because an even multiple would be 360, right? Or 720. Does that equal a -1? No, that would be a +1. So I can't have 2, 4, 6, etc., etc. It has to be 1, 3, 5, on and on and on and on and on. Oh. So now we'll write it as our zeros and poles, our characteristic equation. When we bring that up, we have the poles plus K times the zeros. This tells us something really, really important. Do you remember the entire semester and even last semester when we defined pole zero maps? How many poles do we have? We might have a lot, right? How many zeros do we have? We have the exact same number of poles as we do zeros when we include infinites, right? Doesn't that say right here that if K is equal to 0, right? So this is equal to 0, then the roots of my characteristic equation are the poles. If K approaches infinity, then you can ignore those, and the zeros or the roots of my characteristic equation become the zeros. So start at the pole and end at a 0. This is really important when we draw a root locus. It's a mantra. We start at a pole and end at a 0. Which means whenever we draw a root locus, and I'll draw a simple one over here, that's a pole, that's a 0. We're going to start at our pole, and as K increases, we end up going to a 0. All right? So every root locus has a starting point of a pole and has to terminate at a 0. All right? It can't terminate at another pole. It has to terminate at another 0. So start at a pole and at a 0. That's our second really, really, really important rule. And it helps you when you identify your root locus. It'll help you when you're starting to draw pictures of it, especially when you leave your j omega axis, not the j omega axis, the real axis, and it starts going up or down. You can go ahead and see that. All right, I'm going to end it from here because we're struggling today. But is that a valid statement? Or keep in mind, you still have 8 classes to go. Well, 7, not counting this one. So we got to keep our heads in the game, right? We got to keep cranking. So we got to show up, because just because we're towards the end of the semester doesn't mean we can take it easy. We can slow down a little bit of the material, but a lot of the stuff that we did today, I mean, I know it's confusing, there's a lot of setup, but really all we did was algebra, right? Just did functions and not functions and trig. We just did trig. We did SOHCAHTOA. We did multiplying and dividing complex numbers. That's really all we've done. I mean, it might look a little confusing in terms of the approach, but essentially that's what we're doing. Okay, so when we set up the root locus, you'll be able to go ahead and do that. All right, any questions? All right, well, if there's no questions, have a great day and show up with more energy on Thursday. Take care, everyone.